Good morning, everybody, and thank you for joining us to this online presentation offered this morning by Cheng. Two issues, if I pronounce correctly. Apologies, Cheng, if I didn't.
That's pretty good.
Thanks. As you know, we are just setting this presentation as part of the online cycle that we are organizing within the Quantum Technology Initiative at CERN. And the inspiration is just to offer people like Cheng, I mean, young researchers or researchers in the earlier stages or making the PhD work, as it is the case today, offering opportunities just to showcase your work to other people. So the participants may be peers of you, I mean, students also like yourselves, but it could be also people working in industry, looking for possible, looking for offering possible opportunities also for the presenters. So I think it is a good occasion for you to present the work, and Cheng is doing it today. Now, just few logistics questions, a few logistics points. I think is that we are getting this presentation recorded, but this you have noticed by now. So we will offer access to this recording in the next few days. It's just a matter of processing the video and making it available through the Indico pointer that have made you come to this entry today. Cheng is telling me also that he will offer us a copy of his slides, so you will find them also in the same place. And last thing that I have already checked with Cheng is that you can raise the questions anytime as they come. But what I propose you is that if you please use the chat and use the hand raising, so we don't interrupt Cheng while he is talking, and I will try to manage that. Okay. So thank you very much, Cheng. Your chance, your time.
Thank you, Miguel. Quickly sharing the slides. Okay, I hope they are visible, and you can also see my cursor. Thank you very much for the kind of invitation to give a talk here. So to just briefly introduce myself, I'm Cenk Tüysüz. I'm a PhD student at DZCQTA and also at Humboldt University of Berlin. And today I will be talking about our recent work called Classical Splitting of Parametrized Quantum Circuits in collaboration with my colleagues that you can see here. So in my talk, I will start by talking about parametrized quantum circuits, variational quantum algorithms, and some problems that we have with those. And in the second part of my talk, I will come to the meaning of what classical splitting is and why are we interested in something like that. So, and as Miguel said, please, if you have questions during the talk, just write them in the chat and we can go on. Okay, so variational quantum algorithms. So some of you might have heard of them, and I just want to briefly mention what they are and also like remind you. So variational quantum algorithms are quantum circuit models that we have, and in these quantum circuits we have parametrized gates. So imagine we have rotations and like other gates that we can parametrize, and in the end they represent a parametrized circuit. Our goal is to measure these circuits in such a way. This can be just getting a single sample or measuring an expectation value. In the end, what we have is a function that is parameterized by these parameters. And after this function, we can go to a cost function, and this cost function can define our problem. This can be a classification problem, so just classifying dogs and cats images, or you can also go to some physics problems and try to simulate some physical phenomena. But then when you have this cost function, we have a classical optimizer that we can use to look at the cost function and tune our parameters such that we get to the optimal cost that we want and then solve our problem. So this is the general framework of such quantum algorithms. And what do we need to do with when we are using these algorithms is measuring some expectation values. What does this mean? We will be collecting some samples from this quantum circuit, and in the end, we will have an expectation value. And here, as you see, we have this Hoeffding's inequality that defines how many number of samples one needs when we are estimating an expectation value, because we need to run this quantum circuit a set amount of time, because we cannot really do this an infinite amount of time. And this will give us an epsilon precision. And here this inequality tells us the number of samples we need scales with 1 over epsilon square of the precision that we have. So if you want to go to a very fine precision, you need to have a lot of samples. But in variational quantum algorithms, like what is a good precision? How do we define this? So this is a question now we will try to answer, because in some algorithms, it might be enough to say, okay, 0.1, like it's just a value, you choose it and you are good to go. But can we do something like this for any variational quantum algorithm? So to answer this, I will go one more step and talk about how we measure gradients, because this is the thing that will define our precision. So when we are using these variational quantum algorithms, I told you that we use the optimizer to tune the parameters. And what optimizer does is it looks at the cost function and computes the gradients, if it's a gradient-based optimizer, based on these parameters. And this is the way that you do you compute these gradients with quantum circuits is called the parameter shift rule. And in its most generic form, the parameter shift rule can be defined with this equation that you see here. What you do is you shift the parameter by pi over 4r, and also minus pi over 4r in 2 directions. This is like the finite differences rule that we have from a lot of fields, like just to like compute the derivative, and then you multiply with r, which gives you the gradient in the end. And for some simple rotation gates, you can so this r turns out to be 1 over 2. So what you do is you just add pi over 2 and subtract pi over 2 to obtain this gradient. And for some more complicated parametrizations, you can check the literature if you're interested, and you can go to this paper from Crookes, and you can find more details about this. But coming back, so let's have a look at what these gradients are and how do they look like. So if I take an example 4-qubit circuit with 4 layers, so like I didn't give the description of the circuit here, but it's not really important. What is important is, so here I'm collecting the gradients of a single parameter with some random points of the circuit. And I'm plotting a histogram of them. So you see on the y-axis, we have the count. On the x-axis, you see the gradient values. So we see that they are centered around 0, and it's the distribution that we see. So in this case, to be able to estimate this gradient, you need to have a precision that is able to distinguish these values. So here, if you have, let's say, a precision of 1.0, then you won't have enough fine spacing, and you won't be able to get the right gradient and go to the right direction when you're optimizing your parameters. So you need a much better precision. So in this case, maybe by just looking at the spots, 0.01 or something like this. And you can also obtain the variance, and you see that the variance is, in this case, 9.3 times 10 to the minus 4. So this is a precision that we would be interested in. So what happens if we increase the number of qubits and still look at one parameter? So then we look at the lower plot and see that with the same bin size of a histogram, this time our gradients are getting narrower and narrower. And if you look at the variance, so now we are talking about a variance of 10 to the minus 8. So going back to the Hoeffding's inequality, now you will need like the multiplication is 10 to the 4 times, and remember there was an epsilon square. So if you want a precision of 10 to the minus 8, now you need shots in the order of 10 to the 16. So this explodes pretty quickly. And this will become a problem when you are using variational quantum algorithms for whatever problem that you may have. And we call this problem as Barren Plateaus in the literature. So by defining this more generally, so Barren Plateaus are the exponential decay of gradients with respect to a hyperparameter of the model. This can be number of qubits and number of layers, and it was first introduced to the literature by McLean and others. So you can go check this paper out. And what this paper says is when we have such large and deep circuits, we see that the gradients are centered around 0. And then we can look at the variance of the gradients, as I showed you, to look at how flat the landscape becomes. And here we have some more examples coming from directly this paper. You see again, this time the variance of the gradient. So instead of plotting the histogram, we can just look at the variance. This will be the precision that we need to go to. And you see that this is a logarithmic scale. And on the x-axis, we have the number of qubits. And with increasing number of qubits, our variances are decaying exponentially. And this is quite a bit of a problem. We also see this with increasing number of layers. So here, the thing you can notice is, so each color here represents a different number of qubits. We still see this decay in number of qubits. And with more layers, what happens is you first see a decay at the beginning, and then it saturates to a value. But overall, with increasing system size, you still get this exponential decay. And then as a result, we need methods to cope with this, because as it is now, we cannot really use this for analyzing physical systems and like large simulations of other things. Or if you want to take a machine learning model and scale it up as it is, it won't work. So what are the reasons that we see such exponential decays? So let's first talk about these. So one of the first reasons is the global cost functions. So researchers show that if you employ a global cost function when you are measuring your quantum circuits, you will see the Barren Plateau irrespective of how many layers you have. So even if you have a constant depth circuit, you will observe Barren Plateaus, meaning you will see this exponential decays. So what happens if you go to the local cost functions? So in the local cost function regime, we have regions where we can avoid Barren Plateaus. So you can see by the green regions here, up to logarithm n depth, these circuits are fine. But as you continue and go up to deeper circuits, you will still reach to the Barren Plateaus. So this means that going to high expressivity circuits by adding more layers are leading you to Barren Plateaus. And talking about expressivity, on the center of the slide, you can see I also have a specific part for expressivity. So this is another paper talking about how expressivity is contributing to Barren Plateaus. And here they are analyzing what happens if you correlate your rotations and looking at if this can help you avoid the Barren Plateaus. So when you correlate your rotations, meaning that, let's say you have a single layer of RY gates and you choose them to be the same parameter. So instead of having 5 parameters, you just have 1 parameter and you rotate them all on the same direction. So if you do this, they show that the variances are increasing in size and you can go to a regime where you don't have Barren Plateaus. But this of course comes with a cost of losing the expressivity. So there is a trade-off between how expressive the circuit is and how large you want your variances to be. Another point is entanglement. So the entanglement growth in the circuit has been shown to also affect the Barren Plateaus. Like, one can also argue that the entanglement and expressivity are connected in this sense, because we know that high expressive circuits are also like highly entangling, but we can also like look at entanglement on a like separate tab, and like here this reference that I put here are talking about in the context of quantum Boltzmann machines, and when you have volume of entanglement, your model will exhibit Barren Plateaus. Last but not least, the noise was also shown to lead to Barren Plateaus, and this is quite different from the expressivity, entanglement, or global cost functions, because this is not immediately coming from the feature of the circuit, but coming from the hardware itself. So even if you have a shallow circuit that doesn't have a Barren Plateau, then under hardware noise, it was shown that this might lead to some Barren Plateaus, and we see here that the variances are decaying under this condition. Of course, there are also methods suggested in the literature to cope with them. So the first thing you can do is to choose a circuit that doesn't have Barren Plateaus. So for example, here the example of quantum convolutional neural networks, or also called QCNNs, have been shown to not have them because by their design, the depth of the circuit is logarithm depth. So like if you go back just one slide quickly, we can see here that the local cost function with log depth was already fine for avoiding the Barren Plateaus. So if you want to use such a circuit, then it is fine. But what else we can do? The most used method to avoid or mitigate them is about how we initialize our circuits. So we can find many examples in the literature about some good initializations that doesn't lead to Barren Plateaus, or if you are able to pinpoint a good initial point for your circuit, then meaning that if you are already close to where your global minima is, then the flattened rest of the loss landscape is not really your concern. So then if you are able to point to that location on the loss landscape, then you can go and find your minimum. But this, of course, in general comes with some classical computation. And we are also looking at what is an efficient way to do this, because we still want our method to be scalable. And when we want to run these models at like thousands of qubits, they should still be able to also like classically initializable in this sense. And I also added another method here. So this method is introducing the notion of weak Barren Plateaus. I won't go into the detail of that so much, but here what they are suggesting is you can keep track of the parameters throughout the optimization to keep the variances under control. So this is also a method that one can do. And the figure here shows by choosing the range of our random initializations of these circuits, you can also control the variances. So epsilon here is a coefficient of our uniform distribution. So imagine we have a uniform distribution between 0 and 2 pi, and epsilon is the coefficient. So if it's 1.0, it corresponds to between 0 and 2 pi. And we see that in such a scenario, the variances with increasing number of layers go to smaller values quicker. But if you choose a smaller range, 0.1 or even smaller, 0.05, the variances are much larger. So this is a like very straightforward method that one can use, and like actually this doesn't require a lot of computational resources. But then if you want to keep track of this throughout optimization, then it might get a little bit expensive. So one needs to be careful. So until this point, I talked about what's in the literature about these, and now I want to switch to our suggested methods, and if this can really give us a benefit. So maybe I can just take a moment here to see if there are any questions. I'm not hearing anything, so I guess no. Okay, then, so here comes the classical splitting from the title of the talk. So we are introducing something we call as classical splitting. And this means that you take a parametrized quantum circuit and you split it. Splitting here means you don't allow any operations between them. So no CNOTs, no other 2-qubit operations between them. And we restrict all of these circuits to n-qubit local circuits that sum up to n qubits in total. So we still have an n-qubit quantum circuit in the end. And if you write down the cost function, it is also like trivially obvious, but I want to mention it here. You can write this sum. You can write this expectation values of this complete circuit as a sum of the expectation values of the smaller circuits. So this gives you the flexibility of being able to like run these circuits independent of them. But of course, if you want to have some Hamiltonian terms when you are measuring them that is interacting, this won't be possible. So we are at the moment just restricting ourselves to observables where we only act on these m qubits. So this is a restriction that we start with and we will generalize. So then if you take this ansatz and look at the variances of this, how does it look like? So we know that if you have a deep circuit larger than a logN depth, we will lead to Barren Plateaus. And I write this down here, and this was coming from the literature that I also showed a couple of slides back. So the variances are decaying exponentially. So, but what happens if we consider this classical split ansatz with m being a logarithm function of the total number of qubits? So if you write it down, you see that it becomes a polynomial decay. So from the exponential decay, it's a good choice of m, a local number of qubits, we can make this polynomial. And here on this plot, we are showing this with some numerical experiments. On the x-axis, we have number of qubits. On the y-axis, I have the variance. So let's start with the dashed line, which is the standard case where m is n. So your local number of qubits is equal to full, meaning you don't have any splitting. So, and you see that the dashed line is going down exponentially as our y scale is a logarithmic scale. And then for small number of qubits, we can assume m equals 4 to be the approximation to the logarithm of number of qubits. And you would see that the blue line is not showing this exponential decay as compared to the dashed line. So this gives us a motivation to use such models and not lead to Barren Plateaus. But of course, this has the cost of reducing the expressivity, because now you have smaller groups of circuits rather than one large circuit. So to test this idea, we start with tests on a classical data set, which is a synthetic data set that we generated. And here what we have is, we have 3 data sets. These all have different sizes. So here n is number of qubits, but also the size of the data set. So we choose a data set with 4 features, 8 features, and 16 features. And then we train the quantum circuit with classical splitting and no classical splitting. So no classical splitting means that m is n. And so we can track the accuracy of such models on this plot. So let's have a look for n equals 4. So for n equals 4, m equals 4, this is the no splitting model. The accuracy is around 80%. And if we go to higher system sizes. For n equals 8, we need to look at m equals 8, and this is the square, the red square, and we see that the accuracy is going down to 0.75, and with increasing it one more time, n equals 16, we see that the accuracy is now around 70%. So this is coming from the decay of the variances affecting our training. So this is the standard case that you would see if you have a deep circuit, and here I only considered a linear depth circuit. And now let's look at the m equals 4 model that I showed the gradients of. So if we follow m equals 4, in the n equals 4 case, they are the same. We can skip that. So n equals 8, we will be focusing on the green triangle. So if you look, the accuracy is pretty much the same, around 80%, and n equals 16, again, 80% accuracy. So by using classical splitting, we managed to preserve our accuracy. Since we are not really doing something new, we are not able to go to higher accuracies that is expected. But what we did is now we have larger gradients, and we managed to keep the model's trainability without damaging any other feature. So this is the take-home message from this, that on the classical data set, we are able to manage the trainability and preserve it. Here on the slide, I put some more details, and here we also have a comparison with no Barren Plateau ansatz. So here I'm showing again the same, like results from the same data set. Everything is the same. I'm just showing you the learning curve this time. So if we look at a shallow ansatz, meaning I only have 2 layers, and this is a shallow circuit, so it won't be affected by the Barren Plateaus. And if we look at the trainings, we see that the m equals 16 case, so this has the magenta color in the training loss. Yes, it is slightly slower, but it is still managing to go to some relatively close loss values. So it is not very much affected from increasing system size. But if we go to the linear depth, we see a much bigger difference. So you can notice a difference of the magenta and the green here, and how m equals 4 is outperforming the m equals 16 case this time. So what we see here is the benefit of the classical splitting. And I also have a plot of the loss landscapes. So these are obtained with PCA. So they are not exactly showing you the loss landscape, but they are meant to give an idea. So the first column we have is the shallow ansatz. And with increasing system size, we see that the colors are getting closer to each other. So this means that we want to see some minima, maxima. So we want a loss landscape where we have all of these. We lose the color gradients a little bit, but we still have some minimas and maximas. If you do this for the linear depth ansatz, you'll see that with increasing system size, so now we are looking at the middle column, with increasing system size, we stop seeing any other color and just one flat color. So this is clearly showing us that the Barren Plateau effect here. And the last column shows us the same ansatz, deep, linear depth, but with the classical splitting. So this time you see that we are not losing the minimas, and we still have the loss landscape that we desire, and there is no flattening, as we saw with the middle column. All right, but as I told you, this comes with a cost. So now we splitted our circuits to smaller circuits, but then if you can always have logN number of qubits with smaller circuits, then why do you need quantum computing? We can also do this classically when we are talking about logarithm number of qubits. So to answer this question, we go into a different kind of problem this time. So this comes from quantum machine learning for quantum problems. So for classical data, it's a different case. We already have quantum machine learning models, and you need a good argument for your quantum machine learning model to replace a classical machine learning model. But when we are talking about quantum problems, meaning this can be classifying states that you have already on the quantum computer or simulating some physics, then it is a different story because it is already the home turf of QML models. So now we are interested in what we can do with classical subdividing for quantum problems. So let's have a look. And here we are interested in the entangled dataset. So this is a publicly available dataset that you can find. And also there's the reference describing this dataset and how they obtain it. And I recommend you to have a look at it. And it is actually one of the few publicly available datasets to work with some quantum states and do some classification. So it is a good test bed. Now, in this paper, there is the use of concentrable entanglement, which is an entanglement measure as described here. We don't need to go into the details of this, but what is important is, based on this measure, we can create some separation between states. So here you see on the right plots for 4 qubits, we have a set of states with different concentrable entanglement values. So they are all centered around different values, and our purpose will be to able to classify the states and put them in the right class. And we also have something similar in the 8 qubit case. So now we will be using these states and try to classify them and see in this case if classical splitting can show any benefits. So we have to stop at 8 qubit here because the data sets didn't have 16 qubit examples that we can use. So the improvements will also be marginal because of this. As I showed you also in the plots, that the difference between these two types of models comes from increasing the system size. But let's have a look. So it looks like a complicated table, but do not worry, I will walk you through it. So here we have 4 different problems, and we start with 4 qubits, and the classification task is between 0.05 versus 0.35. So our circuit has depth 4, and we run models with 1, 2, and 4 M values. And in this case, we see very close results actually between m equals 2 and m equals 4. There is no clear separation, but using the classical splitting model, although it's hard to say there is a benefit, but at least they are on par. They are showing a similar performance. And then we can also go to another classification problem where this time the CE values are closer to each other. But this will mean this becomes slightly more difficult. And when we go to that, again, we see that m equals 2 is able to match the m equals 4 model. So let's see what happens when we increase the system size to 8. So in this case, now we can also have one more m value. We see that the accuracies are able to go to 100%. And then I'm also showing here the number of epochs needed to reach the training accuracy. So this will be our convergence. And we see that, again, they are very similar when it comes to convergence. And the same happens when we are talking about a harder problem. So here we don't really see at the moment the Barren Plateau effect, defecting the standard case where we have m equals to the n. But what we can see is restricting the circuit to smaller local circuits is not degrading our performance. So this gives us another strong point of how we can use the classical splitting for a quantum problem. But it doesn't end here, of course, because now there is also another question that we can try to answer, and this is simulating physical systems. So when we are simulating physical systems, we are interested in describing a Hamiltonian, then finding its ground state. And what we want to do is to have states that are interacting with each other. And most of the cases, this can be between all of the qubits, not at once. So it's not like an all-to-all graph, but in the end, you can draw a line and go through all of the qubits. But this is not something we had with the classical splitting ansatz that we suggested. So how we can go around this? To do this, we are proposing an extended CS Ansatz. So what we have here now is the first part is still the same classical split ansatz, and then we append the normal layers that you would always get. So we call them like L and T layers. This is just to like give them a variable name. And here, the T layers are now allowed to have any kind of interactions between them in any way that you want to design. And this allows us to reach to higher entanglement entropy states that the classical split layers could not do. Let's see how this looks like. So on the left plot, I will start by, again, going back to the variances. So in this case, let's first focus on the black dashed line. So on the x-axis, we have number of layers. So we are increasing the number of layers. With increasing number of layers, we are expecting the variance to drop down. Again, my y-axis is the variance. And when we have t equals d, we obtain this black line. So t equals d means we don't have any splitting. It is the full circuit. But now if we start to look around different values of L's and T's for a fixed amount of depth. So here, the depth is fixed by the x-axis. We see that the variance can saturate to a value that we choose based on the value. So we see that it is pretty much getting constant for the t value that you choose. So now this is giving us a lot of flexibility when we are designing an algorithm, and this allows us to choose a variance that we can work with. And I talked about entanglement entropy. So on the right-hand side, let's look at how the entanglement entropies look. So here I'm plotting the ReNU2 entropies or normalized with the S-page entropy. So what we are expecting is by adding more layers, our entropy will saturate to a value. So similar to the plot with the black dashed lines, the entropy increases, and then saturates, starts to saturate, and like these are the average entropy. So this means that when you randomly sample from your circuit, you should expect an entanglement entropy of this level. And what happens when we have different values of L's and T's is that you can choose the amount of entanglement that your circuit would have when you initialize it randomly. So now we have a powerful tool that we can use to choose some different levels of entanglement entropy. And if you remember, entanglement entropy was one of the sources of the Barren Plateaus. So by tuning this, we are also going back to higher variances. And now I want to present our results on the transversal field Ising Hamiltonian on a 1D line. So it is defined by this. So we have some ZZ interaction terms and then X term. For this problem, we chose J and H to be 1, but yeah, these are some details. And I will show you results with 12 qubits and 16 qubits to see the effect of system size increasing. And we have results with 100 different runs to show you some like good statistics. So let's focus on the plots. We have fidelities that we obtain after the optimization. On the x-axis, I have the percentage of split layers. So 0 will mean no splitting. So a standard ansatz that you get. And when we go to the right hand side of the plot, we get to a fully split ansatz, which was the initial classical split ansatz that we recommended, that actually we don't want to use for this problem. So let's look at the success rates, because we see that we can get to 1.0 fidelity, which is our target, but many times you also get 0.0s. So if you focus on the medians, which are the triangles, we see that at first we are around 0.5 success rate, but as we increase the percentage of split layers, our success rate is going to higher values. So using the split layers is helping the optimizer to find a good solution. But if you increase it too much, then it becomes a problem, because then your circuit has too little entanglement in it that it's not able to express the ground state of your problem. So it looks like there's a sweet spot that we can try to find here to get the best value. So if I go on, so the left plot is the same. So on the right, I added the 16 qubit version. So here we see that with increasing system size, now the median is at 0 when we start from the standard ansatz. So in most of the cases, you will get the wrong result. But as we increase the percentage of split layers, we see that the median can jump again back to close to 1.0 fidelity and start giving you good success rates. So having this ansatz is beneficial for such a system. But what we see here is that it is actually not that easy for us to pinpoint this transition point. So in the 12 qubit case, it happened rather quickly, around like 15%, let's say. But on the right-hand side, it happened much later, around 80%. So this is something we couldn't really formalize in the paper, but it looks like there is definitely a sweet spot which might get affected from like many different parameters, but like one can still perform an analysis to find this for a particular system size. All right, so to summarize, today I showed you our suggested model to mitigate the Barren Plateaus that we call classical splitting, and they managed to give us some better trainability and faster convergence in the scenarios that I talked about. Of course, they don't really give you a better result out of the box. They still look some like analyzing the problem, looking at the values and choosing the right hyperparameters. And the extended CS Ansatz showed us that it can improve the performance of a standard ansatz that you have. But one hard thing is still to find this correct sweet spot, the right hyperparameters that give the best results. So if you're interested, you can find this work on arXiv. You can go follow this link. And I would like to thank you for giving your 1 hour for this talk. And if you have any questions, I'm very glad to answer them. Thank you.
So thank you very much, Cenk. Consider yourself with plenty of clappings, only that we are online, so we can offer you the virtual version of it. By the way, I think I have put a link to your paper, or to this paper that you mentioned already also in Indico. For the people who want to make it easy to find it, it is in the Indico link. So the floor is open for questions or comments, or I mean, you don't need to use the chat anymore. You can make yourself the question interactively, but just raise the hand just to keep an order in case. Otherwise, it seems everybody is quiet. No questions. Everything is clear. Okay.
Hi, sorry.
Okay.
I
yes,
have a question.
Please do. Sorry, I missed it.
Did you study the effect on different ways of coupling the different wires? Like if a wire carries some information about the data, which may be correlated to some other wire, maybe grouping them together will be either beneficial or not. Did you study the effect on different configurations of the couplings, or I mean of the splittings? Sorry.
Yes, so this is actually a very good point. We haven't studied it, and like we didn't do this on purpose because we didn't want to give the classical split ansatz an advantage by doing this. So here, when I was talking, if I can just quickly go back, especially for like this problem. So we are considering a like feature size of 16, let's say. And as you said, some of them might be correlated already, but we are blindly splitting them. so that we are not really like making a tailored model, so to say, for this problem. And even with that, you can still preserve the accuracy. That's why we didn't do it. But I believe if you do like exactly what you said, it would help with the performance of the model.
Okay, thank you very much.
Okay, anybody else?
Hello.
Go ahead.
So I don't have a question per se, but thank you so much for your presentation. And the only thing I wanted to say is that there was a comment in the chat asking for the slides. So if it's possible for you to also share today's presentation, we will upload it to the Indigo page, and then everyone can also look through this again.
Yes, so yeah. I will send the slides after the talk, and I think they will add them to the Indigo page. So.
Thank you so much.
Welcome.
Okay, so with this, we consider the session finished. Just again, plenty of virtual clappings to check. And please remember, if you are interested in participating in this cycle, or you know people as well, maybe colleagues who would be interested to contribute their own work or to present their own work, do not hesitate to contact us. The details are already at the Indigo link that you can find. And otherwise, we look forward to have you joining us at the next lecture, which is on the 29th of March. Thank you very much, and have a nice day, everybody. I see the clappings.
Bye.
Thank you. Bye.